In this video, I will explain dot and cross product. Starting with the dot product. Another name for dot product is the scalar product. If we have two vectors, vector A and vector B, the dot product of vector A and vector B is written as A dot B equal to the magnitude of A multiplied by the magnitude of B multiplied by the cos of the angle between them. So this is the formula for the dot product. A dot B equals to the magnitude of A multiplied by the magnitude of B multiplied by the cos of the angle between A and B. We have some notable angles like theta equals to 0 degree. If theta equals to 0 degree, it means the angle between vector A and vector B is 0 degree. So they are parallel to each other. Now, cos 0 is 1. So it means the dot product of vector A and B, when they are parallel to each other, is equal to the magnitude of A multiplied by the magnitude of B times 1, which is equal to the magnitude of A multiplied by the magnitude of B. So A dot B equals to the magnitude of A multiplied by the magnitude of B. So it means the dot product of two parallel vectors is equal to the product of their magnitude, and it is maximum. So this is the maximum dot product when the vectors are parallel to each other. Now, when theta is equal to 90 degree, it means vector A is perpendicular to vector B. Cos 90 is 0. So we have A dot B equals to 0 times the whole of this is 0. So the dot product of two perpendicular vectors is equal to 0. This is important because you can use it to check the orthogonality of two vectors. Two vectors are orthogonal to each other if their dot product is 0. So orthogonal means 90 degree. Another case is when theta is 180 degree. 180 degree means they are anti-parallel to each other, so they are oppositely directed. Cos 180 is minus 1. So A dot B is equal to minus the magnitude of A multiplied by the magnitude of B. So the dot product of two antiparallel vectors is equal to the negative of the product of their magnitude, and it is the minimum dot product. So the dot product is maximum when they are parallel, it is 0 when they are perpendicular, and it is minimum when they are anti-parallel. Now, the dot product in component form. If we know the components of the vectors, we can also find the dot product. For example, if vector A is AXI plus AYJ plus AZK, and vector B is BXI plus BYJ plus BZK. The dot product A dot B is equal to AX times BX plus AY times BY plus AZ times BZ. So that's how to determine the dot product of two vectors in component form. So if you know the components of vector A and you know the component of vector B, you can use this to determine the dot product. AX is the x component of A, AY is the y component of A, and AZ is the z component of vector A. BX is the x component of vector B, BY is the y component of vector B, and BZ is the z component of vector B. Another important thing to know about the dot product is that it is commutative. The meaning of this is that A dot B is equal to B dot A. So that is correct for dot product. A dot B is equal to B dot A. So the dot product is commutative. Now, the application of dot product. You can use dot product to determine the work done. Work done is force dot displacement. So work is the dot product of the force vector and the displacement vector. Don't forget that work equals to FD cos theta, and FD cos theta is the dot product of the force vector and the displacement vector. So it means the work done is equal to F dot D. Another application is to find the angle between vectors. So you can use the dot product to find the angle between two vectors. Let me clean. So we can use the dot product to find the angle between two vectors. We know that A dot B is equal to the magnitude of A multiplied by the magnitude of B multiplied by cos theta. So cos theta is equal to A dot B over the magnitude of A, the magnitude of B. So if you know the components of two vectors, you can determine their dot product and determine the magnitude of the vectors. So you can get the angle using this formula. Cos theta equals to A dot B over the magnitude of A multiplied by the magnitude of B. So that's another application of the dot product. Another application is to determine the orthogonality of two vectors. Two vectors are orthogonal to each other if their dot product is 0. So if the dot product is 0, it means the angle between the vector is 90 degree. So that's another application of dot product to determine the orthogonality of two vectors. Here is a question. If vector A is equal to 3i minus 2j plus 5k and vector B equals to 4i plus j minus k, find A dot B. So we want to determine the dot product of vector A and vector B. Know that dot product is equal to 3i minus 2j plus 5k dot 4i plus j minus k. So A dot B equals to 3 times 4 is 12 plus minus 2 times 1. There is 1 in front of this, so minus 2 times 1 is minus 2 plus 5 times minus 1 is minus 5. So we have 12 minus 2 minus 5, and that is equal to 5. So that is the dot product of A and B. Here is another question. If force F equals to 2I plus 4J Newton acts on a body and causes a displacement S equals to I plus 5J meter, find the work done. So let's do it. We know that work done is the dot product of the force vector and the displacement vector. So the work done is equal to 2I plus 4J dot I plus 5J. Work done equals to 2 times 1 is 2 plus 4 times 5 is 20. So the work done is 22 joule. So that is the work done. The dot product of the force vector and the displacement vector. Here is another question. If force F equals to 5I plus 3J plus 2K Newton acts on a particle and displaces it from its origin to a point P equals to 2I minus J, determine the work done on the particle. Now, to determine the work done, we have to do the dot product of the force vector and the displacement vector. We have the force vector already, so we need to get the displacement vector. Now, since the force displaces the particle from its origin to a point P, then the displacement will be the difference between the final position and the initial position. The initial position here is the origin, and the final position is point P. So F vector is equal to 5I plus 3J plus 2K. The displacement vector will be P minus the origin. Oh, the coordinates of the origin are 0I, 0K, 0J. We have to subtract it from the final position. So 2 minus 0 is 2I. 1 minus 1 minus 0 is minus 1J, which is minus J. The P has no K component. So we can just write 0 minus 0, which is 0K plus 0K. So that is the displacement vector, 2I minus J plus 0K. Now we can now go on to calculate the work done, which is F dot S. 5I plus 3J plus 2K dot 2I minus J plus 0K. 5 times 2 is 10 plus 3 times minus 1 is minus 3 plus 2 times 0 is 0. So 10 minus 3 is 7. So the work done is 7 joule. That's the work done on the particle. Here is another question. If vector A equals to 3I plus 4J and vector B equals to 4I plus 3J, find the angle between A and B. So we want to find the angle between vector A and vector B. We can use the dot product method to find that. We know that dot product of A and B is equal to the magnitude of A multiplied by the magnitude of B multiplied by the cos of the angle between them. So if you make the cos theta the subject of the formula, cos theta will be equal to A dot B over the magnitude of A multiplied by the magnitude of B. So we need the dot product and we need the magnitudes of A and B. A dot B is equal to 3 times 4, which is 12, plus 4 times 3, which is also 12, and that's 24. The magnitude of A is equal to the square root of the x component square plus the y component square, which is 3 square plus 4 square. 3 square is 9, 4 square is 16, 9 plus 16 is 25, root 25 is 5. For b, the magnitude is root x component square plus y component square. That's 4 square plus 3 square. 4 square plus 3 square is 16 plus 9, which is 25. So root 25 is also 5. So it means cos theta is equal to a dot b, which is 24 over 5 times 5. Cos theta is equal to 24 divided by 25, which is equal to 0.96. So theta equals to a cos 0.96, and that is equal to 16.3 degree. So that is the angle between vector A and vector B, 16.3 degree. The next thing is the cross product. The cross product of two vectors A and B is written as A cross B equals to the magnitude of A multiplied by the magnitude of B multiplied by the sine of the angle between them. So this is the formula for the cross product. This formula is for the magnitude. So the magnitude of the cross product of A and B is equal to the magnitude of A multiplied by the magnitude of B multiplied by the sine of the angle between them. Actually, the cross product of two vectors is another vector that is perpendicular to the plane of the original two vectors. So if we have two vectors A and B, if we do the cross product, we get another vector that is perpendicular to the plane of vector A and vector B. To determine the cross products of two vectors A and B in vector form. So if you know the components of vector A and vector B, I want to determine the cross product. We use the matrix method. So I, J, K. So if the components of vector A are AX, AY, and AZ, and the component of vector B are BX, BY, BZ, the product vector is equal to the determinants of the matrix formed by these two vectors. So if you want to determine the cross product of A and B in vector form, we find the determinants. So the product vector is equal to the determinants of the matrix formed by the two vectors. So plus, minus, plus. Now, cross product is not commutative. So we say it is anti-commutative. Meaning A cross B is not equal to B cross A. So unlike the dot product that is commutative, the cross product is not commutative. So A cross B is not equal to B cross A. In fact, A cross B is equal to minus B cross A. That is that. Cross product is anti-commutative. Now, for the magnitude part, if theta is 0, it means vector A and vector B are parallel to each other. Sine 0 is 0, so the cross product is 0. So it means the cross product of two parallel vectors is 0. Now, if theta, which is the angle between A and B, is 90 degrees, sine 90 is 1. So magnitude of A cross B will be equal to the product of the magnitude of A and B. So equal to A, B. And it is maximum. So the cross product of two perpendicular vectors is equal to the product of their magnitude. So that's for the cross product. Now for the applications, you can use it to determine the torque. Which is equal to the position vector multiplied by the force vector. So if you know the position vector and you know the force vector, you can determine the torque using doing the cross product of the position vector and the force vector. It is R cross F, not F cross R. R cross F, not F cross R, because cross product is anti-commutative. So if you switch it, you get a negative value. So R cross F, you have to be very careful. If you are dealing with magnitude, it doesn't matter, but if you are dealing with vectors, you have to be very careful. R cross F. If you do F cross R, you get the negative of this, which is not correct. So the correct formula for torque is R cross F. So that's for the application. Here's a question. If vector A equals to 5i minus 2j plus k and vector B equals to 2i plus 4j minus 20k, find A cross B. To do this, we can use the matrix method. We know that the product vector is equal to the determinant of the matrix formed by these two vectors. So A cross B is equal to, let us write out the components of vector A, 5 minus 2 and 1. For B, 2, 4 and minus 3. I, J, K plus minus. Now, let us do it. For the I component, plus into bracket. Ignore what is under I. Then find the determinant of this minus 2, 1, 4, minus 3. So minus 2 times minus 3 is 6. Minus 4 times 1 is 4. I. Minus, for the J part, ignore what is under K. Then do the determinant of this and this. So 5 times minus 3 is minus 15. Minus 2 times 1 is 2. J. For the K plus, ignore what is under K. Then find the determinant of this. 5 minus 2, 2 and 4. 5 times 4 is 20. Minus 2 times minus 4, which is minus 4. Okay. So A cross B is equal to 6 minus 4 is 2. So plus 2i is 2i minus 15 minus 2 is minus 17. But there is minus in front, so we have plus 17j. 20 minus in the bracket minus 4 is 20 plus 4. So we have plus 24k. So this is the A cross B, which is the cross product of vector A and vector B. As you can see, it is in vector form, where you can find the magnitude. So the magnitude, if you want to find the magnitude, it will be root 2 square plus 17 square plus 24 square, and that is equal to 29.5. So that is the magnitude of this vector. So that's how to do it. Just set out the vectors in matrix and use the determinant method to get the product vector. And if you need the magnitude, you can calculate it this way. Here is another question. Determine the torque of a force F equals to I plus 2J minus 3K Newton about a point O. The position vector of the point of application of the force to a point O is R equals to 2I plus 3J minus K meter. So we have the force vector and we have the position vector. Now we can use the formula for torque. The torque is the position vector cross the force vector. So to find the cross product, we can use the matrix method. So the torque is R cross F. R cross F. So R is first. So 2, 3, and minus 1. F is 1, 2, and minus 3. I, J, K, plus, minus. So let us do the matrix. So I plus. Now ignore what is under I. Then find the determinant of this. 3 times minus 3 is minus 9. Minus 2 times minus 1, which is minus 2. I. For the J, minus bracket. Ignore what is under K, then find the determinant of this and this. 2 times minus 3 is minus 6. Minus 1 times minus 1 is minus 1. For the K, plus bracket. Ignore what's under K and do the determinant of this. 2 times 2 is 4. Minus 1 times 3 is 3. Okay. So let us evaluate it. Minus 9 minus the bracket minus 2 is minus 9 plus 2. And that is minus 7. So minus 6 minus the bracket minus 1 is minus 6 plus 1. And that is minus 5. But there is minus in front, so minus in the bracket minus 5 is plus 5. Minus 7i plus 5j. 4 minus 3 is 1. So we have plus 1k, which is just plus k. So that is the torque. Minus 7i plus 5j plus k What's the unit? Newton meter. So that is the torque. R cross F. Take note, it is R cross F. R cross F, not F cross R. If you do F cross R, you will get 7I minus 5J minus K. So that's for that. That's the end of this video. Thanks for watching.